Today I wanted to talk about planning and models, but in the context of learning. Maybe I should have put it in the title, but just quickly to recap what we've been doing. Last lecture we learned policies directly from experience using policy gradients, methods, and such. Before that we talked a lot about learning value functions, and in each of these cases I said I'll not talk so much about models in this lecture, deliberately, because this is like a whole rich field in and of itself. And in addition, these things can look at in isolation, so then it's good to separate them and to look at the components, to try to understand each of the components separately before going all the way into the complete breadth of what you could imagine. So in this lecture we'll basically revisit models, and specifically we'll talk about basically two, again, kind of separable things. One is where you don't have a model, you have to learn this, you have to use this somehow. And the other one is where you want to plan with a model. And these are related, but they're different in the sense that you could also imagine just having a model. And in fact, when you have a model and you want to do planning, we've already seen a case of that in the dynamic programming lecture, where we were doing dynamic programming as a way to do planning given a model. And that's a valid way to do planning. Of course, there's other ways to do planning, and we'll discuss some today. I will not be able to cover the full width of the field of planning because it's a very rich field. One thing to keep in mind though is that a lot of the classic planning algorithms, they have basically been built for the assumption that you have a true model. And if you don't, then these algorithms might not be the right choice. And I'll discuss why that's the case. This is just refreshing the terminology. So we've talked a lot about model-free reinforcement learning. This covers both the value-based reinforcement learning and the direct policy search reinforcement learning and the actor-critic algorithms, which do both, where the idea is to learn a value function or a policy from experience directly. And to contrast with that, what is sometimes called model-based reinforcement learning is the setting where you don't have a model, again, but you're going to learn it from experience, or you're given a model, and then you plan a value function or a policy from that model. Now the terminology is there's a little bit of a gray zone in the literature. If you search for, say, model-based reinforcement learning and you look at the papers that you find, some papers will strictly look at basically the first case there where there's no model, but you have to learn it, and they'll say this is model-based reinforcement learning. By definition, this is model-based reinforcement learning. Whereas other papers might allow there to be a model, maybe even a true model or an approximate model. So the terminology is a little bit ambiguous in that sense. But it's still a useful distinction to have a shorthand that you can refer to whether or not you're building an explicit model. And this is again recapping what we've seen so far, but it's useful to have this picture in mind. So, yes?
Sorry, basic question. Could you just sort of remind us what exactly constitutes a model?
Yes.
In the context of the kind of problems we've been looking at.
That's a very good question. So, when I say here you learn a model or you're given a model, I essentially mean, or the best way to think about it for now is that you're given an MDP that you can fully inspect. So you can look at the state transition probabilities, you can look at the rewards. That's the simplest thing to keep in mind, although on later slides you'll see exceptions to that. For instance, you might not be able to inspect the MDP, you might just be able to sample from it. In that case, it's more like a black box that you can query, but you can't actually see the actual probabilities, it just gives you a random sample. We would still, in some cases, call that a model. In other cases, we would just call it a simulator. And in yet other cases, we would just call that the environment, depending on whether you care about that thing or whether you care about something else that thing is trying to mimic. So the word model is a bit overloaded. It's actually very overloaded. Word planning as well. But unless I say otherwise, when I say model, you could think of some MDP, which is trying to model the problem that you're actually interested in. It's a good question, thanks. Yeah?
If you're in, say, the Atari setting and your agent literally has an emulator inside it and it can query the next frame, that also, that's obviously more clearly specified than an MVP, but that would
So yeah, so the question is if you would have a true simulator inside, say you're doing Atari, but you have the Atari simulator inside the agents, then that would constitute, in the sense of which we're talking about here, that would constitute a model. In that case, it would even be a true model. It would map exactly to the thing that you're trying to solve, in which case you never have to collect real experience again. You can just do all the thinking in your head, do the planning, if you will. And this again shows that there's a little bit of a gray area here, because then what is the distinction? Well, it depends what you use for planning. You could just query the simulator inside your head and you could still use a model-free algorithm to learn from that, which means we're using, for instance, Q-learning to plan, which is a valid thing to do. Is that model-based, model-free? It kind of depends where you draw the boundary between the agent and the environment. So some of these things are definitely ambiguous, and that's okay, right? But it's good to keep in mind that they might be. So the distinctions aren't always that clear. It's somewhat clearer when you think about the case where there's an external environment that you really don't know, and you're going to construct a model inside, and you're basically going to accept that this thing is going to be approximate. It's going to be not the true MDP, but then you're going to try to use this somehow. So now there's an explicit representation of the outside world, of the environment that you're trying to solve, and you're trying to use that in some way to come up with a good policy. Okay, so this is just your general overview of, or at least one way to look at reinforcement learning as a whole. So more or less where we started all the way at the beginning was at the top left corner, where we talked about dynamic programming as a way to solve Markov decision processes. And specifically we talked about these one-step updates, where you basically plan one step into the future, and if you do this for the true value, if you just write down the true value of a state as a function of the one step in your model, in the true MDP in that case, into the value at the next state, then this constitutes the Bellman equation. So that's just the definition of what the value is. And then we talked about that it's also possible to define the optimal value in that way. And then we talked about using that equation, the Bellman equations, to basically define updates, where you, instead of plugging in the true value function, which you don't know, you plug in an estimate, and then it turns out if you keep on doing these one-step rollouts and using your estimate, you'll converge to the true values. That was dynamic programming. Then we talked about basically the bottom left corner, temporal difference learning, which is basically a sample-based version of dynamic programming. We sample a one step, and then turns out if you do that sufficiently often, you can still get the same answers that dynamic programming gives you, but you don't need a model. We also talked about Monte Carlo learning on the bottom right, where you do something very similar. You sample, but instead of using the estimate, the state value at the next state, you're going to sample a whole trajectory, say, for instance, for a given policy, and you use that to approximate your value. What we didn't talk about that much is exhaustive search, because it basically is too big. So that will be the version where you use your true model to basically plan through the whole tree, but you go all the way to the end. So you're not using any value estimates along the way. But of course, you don't have to go all the way to the end. And this is a little bit of maybe a straw man. And a lot of classical planning algorithms actually work a little bit closer to that space, where we are constructing at least part of the tree. Maybe not just a single step, but we might go a couple of steps deep. And then we still might use a value function somewhere along the way, which means we're maybe somewhere along the center of this thing, especially if you also roll in sampling. And I'll talk about how to roll in sampling when you do that. So you could imagine combining a model and a sampling-based approach, and this can be actually very useful. So just to remind ourselves, the difference between top and bottom here is whether you use the model or whether you sample. And one thing that I'm saying is you can go in between. You can use your model a little bit, and then still sample. The other dimension is whether you use a one-step look-ahead or whether you use full look-ahead. And we actually talked about this quite a bit when I said you could do multi-step updates, where you do a few steps and then you bootstrap. And you can even have mixtures. I didn't talk about that much, but there's this lambda parameter there at the bottom, which basically says you might bootstrap a little bit. You might look a little bit at the evaluation at a certain state, but you might also still roll forward from that state and then mix the sample-based value from the learned value at that state. So this is the full space, and now we're going to try to go a little bit somewhere within that space to find algorithms that might usefully combine properties of these extremes. And so first, to remind ourselves, this was the classic example that I've shown many times. The agent takes the action, the environment sends back an observation, there's a reward somewhere, which you could think of as coming from the environment if you please. So the difference now is that we're going to basically inject a model in there. So you're still going to act, but the experience now goes into the model rather than into the agent directly. And then we use the model to inform our value or our policy. So there's this indirection now. You could still have the direct loop. So basically this loop here on the top right is basically the same loop as you've seen before. But now there's this additional loop which basically sits inside the agent, if you want, where you build an additional representation of the world out there and you use that to additionally augment your value or your policy. Now intuitively this already sounds like it could be a good idea, because by trying to learn to model the outside world, we might just be learning more about what's happening there. If, for instance, if your values are fairly non-informative about everything that might be happening, you might be learning specific values, but it might be hard to generalize when you go to a new situation and you don't understand the rules. So to give you a somewhat abstract example, you could imagine if you go to a completely new situation where your vision is different, your value function might be completely wrong, but if you know the laws of physics, you might still be able to figure out that if you toss a ball in the air, it will drop down, even if you've never seen a ball of that color or of that size, and so on. So it does make intuitive sense that you sometimes want to learn a little bit more than just a policy or just a value function, and maybe that more is then or could then be a model. Okay, so that's the high level. Now I wanted to make it more concrete. And we'll just be very explicit about what a model is. A model is, in this case, a Markov decision process. It doesn't have to be, but this is how we're going to define it for now. And to keep things simple, I'm going to keep the state space and the action space the same. So the states and the actions are the same as those from the environment. That's not necessarily the case, but it's just for the simplicity of the exposition here that I'm going to stick to that case, which means that the model is then fully characterized by the transition function and the reward. And that's what we're going to learn. This little p, you can see it in the equation there. This is the same equation we've had before when we were just talking about Markov decision processes in general, except that there's now a little hat on the p and there's this eta subscript. The eta are the parameters of your model, because we're going to typically consider parametric models. It doesn't have to be, could also be a non-parametric model in a sense, in which case maybe the eta is replaced by data. Instead of parameters, you have data that you're using. But we have some approximate model, and the idea is that this model somehow approximates the true model. I'm already going to call out here that this is only one thing you could do. You could imagine that the true model is too complex, and sometimes it might be useful to construct a model that's not actually the true model, but something that is still useful. But I won't go into too much depth in that. But that's an interesting research direction. So we're going to assume that the states and actions are the same, which means that we can basically just learn these things. And we could also think about learning them separately, which might be simpler in some cases, where you basically try to learn for each state action what is the expected reward, and for similarly for each state and action what is the next state. Yeah.
Sorry, can you go back to the slide?
Sure.
I'm just trying to understand this. So in a small grid world, what would be an approximation to the actual probability?
So in a grid world, what would be the approximation? So
Because we're estimating the probability anyway, right? For everything we're doing. We don't know the probability.
yes, we don't know the probabilities. So the question is, how do you then? Maybe there's multiple questions. One is, how do you learn this? And it's good to have a concrete example. So we could say, for instance, in a grid world, what would be the goal of this learning this model? Let's take the simplest example where the grid world is completely deterministic, which means that when you, for instance, press up in a certain cell in your grid world, you'll deterministically go to the cell above it. Then what you're trying to learn here is that the next state for any state where you press up is the state above it. And maybe additionally you want to learn that whenever you try to do that when you're just below a wall, then it's actually the same state again. You could imagine learning this quite simply in a simple small grid world. Of course, if it's a very complex domain, you want to generalize somehow, so maybe this model is then something that generalizes as well, such as a deep neural network, so that you could also query it for states and actions that you've never actually seen, and you hope to still get a relatively reliable answer through generalization. And actually here I'm going to make that a little bit more concrete. So we're just going to collect some experience. This could be from multiple episodes, so I'm not making distinctions here between where the episodes end or not end. Of course, you need to be careful about that if you want to implement something like this. And then we're just going to note that this experience can basically be transformed into a data set, where you have a state and an action as an input, and as the output you have the reward and the next state that you've actually seen in that situation on that time step. And one thing that you can do is then to learn a function that basically tells you what the expected reward and the expected next state is for a given state and action. Now you can pick a loss function. Maybe you could have separate loss functions for the reward or the state, or you could merge these somehow. You could also have separate functions for the reward and the state, each of which has their own loss function. And for instance, maybe you have something like a mean squared error. Whether that makes sense depends a lot on the specifics of the domain. For instance, if you think about the Atari games, you can question whether it makes a lot of sense to put a loss on the pixels of one frame versus the pixels of another frame, whether you want to do this pixel by pixel, or whether it makes more sense to maybe try to find some features of the screen and then try to define a loss in that space. That's non-trivial in general, and I won't go into much detail on how you should pick that loss because it really does depend. But it's something to keep in mind when you want to construct something like this. But whatever loss function you pick for this model, you then minimize the parameters of the model so that you find this function that maps these input states and actions to these outputs. So in this case, if you do it like that, where for instance you pick a mean squared error, then the output would be an expectation model. That's fine in a sense, but there might be certain things that are limitations of this. Before I go there, let me just quickly stop here to see if everybody's on board. If you have any questions, please interrupt. Okay, otherwise I'll continue to the expectation models. Because they might have certain disadvantages, and one way to see that intuitively is that you could imagine that there's an action and it randomly transitions to one of two states. In one state you went to the left of a wall, and the other you went to the right of a wall. So note, I'm not talking about the action going left or going right. There's this one action that you do. You give a certain decision to, say, your motors, and it just so happens to be the case that in 50% of the time you end up to the left, and 50% of the time you end up to the right of a wall. Maybe because there's additional safety controllers or whatnot that basically prevent you from going into the wall, that you don't have control over, that are basically, as far as the learning algorithm is concerned, they're part of the environment, but they are there and they do result in you not hitting the wall. So you can imagine then, if you're, depending on the loss you have on your next state, that the expected next state might be exactly in the wall or against the wall, which is a state you might not actually end up in. So if you think about the grid world, maybe that's an easier example to think of. If your expectation, if you have random transitions on these grids, and let's say that if you press up, you don't actually go up ever, but you go diagonally left up or you go diagonally right up. You could imagine that the dynamics work like that. And let's say that you're just below a grid in which there's a hole. Then pressing up would mean, in all cases, you would never end up in the hole. But if your loss is such that you try to interpolate between your position, you would end up exactly in the hole, which is a state that you never actually end up in. And the reason is that we're discussing expectation models here. And the expected state might not actually be a state that will ever happen in reality. Now, so this might seem that this is a problem for expectation models, and it could be. But for linear models and values, this turns out not to be so much of a problem. And you could take this in two ways. One, you could take this as meaning that we should be doing linear values and models, where maybe the features are themselves nonlinear functions of, say, your observations. but then you have a linear model on top of that and a linear value. Or you could still take this to be just a limitation of the expected models, and it really depends on what you want to do in terms of concrete algorithms. But just to show you that in a linear case it's okay, so what I've done here is I've basically replaced the states with features. So we assume for now we have some fixed feature function that takes a state as input and then turns that into a vector, phi. We've done that before as well. So there's a shorthand here as well, where phi subscript t means this is your features at state st. And then of course phi t plus 1 is the features at state t plus 1. Now if we would build an expectation model on these features, where again the interpolation may or may not make sense in terms of the actual features you might see, then we might note, if we have a linear model, that this is basically just a matrix multiplication. We take the features phi t, we multiply a matrix P that we're going to learn, potentially, and the output of this, the semantics of that, is that this is an approximation to the expectation of the features at the next state. For now, we can even assume that this is exact. You've learned this model, or this model is given to you. You have this linear model, and it actually gives you the expected next features, just for simplicity. And let's assume that we also have a linear value function, which is parameterized with some parameter vector theta, which we might be learning, which means that the value at st is the dot product of this vector theta with the features at st. So features subscript t. Then we can just write it out, and we could talk about what is then the expectation of the value of the state after a couple of steps, or even after one step, but I did it here for after n steps. And we can just write that out because we know going n steps into the future with our model would mean we just apply this matrix P multiple times. But you can go through these steps yourself one by one if you want. But the main point that we're using here is that the expectation commutes with the linear operation of the matrix. So what essentially happens all the way at the bottom is that we're able to push the expectation all the way through inside, and instead of talking about the expected value of some state in the future, we can talk about the value of the expected state, in a sense. So that's what we've done here. Actually, the notation there at the end is a little bit, that should have been the expected state, not the expected feature now, because I gave states as input to the value. So for linear values and linear models, because the expectation commutes with linear operations, basically expectation models are fine. But this might not hold in general. When, say, the value function is nonlinear, you cannot push this expectation through the value, in which case these things are not necessarily the same. And typically we are interested in the expectation of the value of a state after multiple steps. But we don't have it because the only thing our model can compute is the expected state, and then applying the value to the expected state is no longer necessarily the same as the expectation of the value at that state. So is there an alternative? Yes, first question.
Could you give us instance about like what feature that could be?
Sorry?
Could you give an example about like what feature that could be? Like
So a concrete example. So that's a little bit harder to do on the fly. I mean, the examples that I gave don't all go through because in that case you actually want to have something that's nonlinear. I'd rather just think about that a little bit and then give an answer later for a concrete example. So first, let's discuss the alternative. So what else could you do? We might not want to assume that everything's linear, and in that case the expectation model might not be sufficient because it gives you expected states that might not actually be real states, and then it might not make sense to, for instance, feed those expected states back into your model, which expects real states to iterate on, and it might not make sense to feed these expected states into a value function, which also might be trained only to give you valid answers for real states. So what else can we then do? Well, one potential possibility is to build a stochastic model. something that is trying to basically output rewards and next states that are valid reward and next states in a sense, but it's not committing to exactly giving you just one. It basically gives you the whole distribution. And one way to do that is to use a stochastic model or a generative model, as they're also called. And how I denoted that here is that there's this predicted next reward and next states, which are now samples. And the input to the model is omega, which is a noise term, which means that if you would query this model again, you would resample the noise term, and you might get a different sample for the reward in the next state. Now, this reward in this next state, they will have variance, right? Because if you sample them again, you might get different answers. But the idea is that each of these next states are actually valid next states that you could put into your model again. And thereby you could create a whole trajectory, which is basically very similar now to a Monte Carlo rollout in the real environment. But instead of using the real environment and querying that to give you random states, you're querying your stochastic model. Yes?
So in this case, p hat is a function, right? Because otherwise you would have a condition on these.
In this case, yeah. So p hat now here is a function. That's a good question. And it can be a function. It doesn't have to be a probability distribution because I have this noise term that I also explicitly give as an input. And therefore, the output of the function can still be noisy.
So that's an actual equal sign, is not like.
It's not a sample from. It's an equals. But I should probably subscript omega also with some index because you're going to resample that thing every time you query this. Not necessarily once for every time step. You could imagine querying it multiple times at the same time step. But you might put in different, or you would put in different noise terms for every time you sample it. Typically, when you actually implement this on a computer, typically you would just put uniform noise in there, and somehow internally this gets transformed to the right noise that you need to have your generative model. Yes?
Could this be equivalent to the sort of the earlier linear model if that linear model were like a logit and you're sampling from that logistic output?
So could this be equivalent to the linear model? So this is already, in some sense, even the types don't really match because this one does take this noise term and it depends on the noise term, where the linear model just gives you one answer. Every time you query it gives you the same answer. So in that sense, it's already not the same. There are, of course, edge cases in which you can make these things to be basically equivalent. One version would be where you basically you just ignore the noise term and maybe your loss function still makes it so that then the output will be the expected state. And if your model itself is linear then as well, then you just have your linear model back. So definitely, in some case you could say that the linear expectation model is a special case of this one, but this one's more general because it can use the noise to basically try to match the whole distribution of next states rather than just trying to output one specific next state. The example I already mentioned this, but just to reiterate that, the advantage of this is that you can chain these. The output sampled state is a valid input for your model again, so you could create a whole trajectory instead of just having this single output expected next state that you then cannot really put into your model again, except if it's linear. However, there is noise introduced, which might be a downside in some cases, because it might mean that your samples have more variance. So one consequence of this is if this is a fairly expensive function, your outputs might have high variance. If it's a cheap function, you might be able to mitigate that by just sampling it multiple times. And then you create maybe a whole tree of outputs.
I'm still confused about the noise term.
Yeah.
Is it something that comes through, do we manually add this, or does it come from exploration of the model?
So the noise term is a good question. So where does it come from? How is it used? So this is basically just a way to turn something that you want to be stochastic into a proper function. It's just now a function of its inputs. It has nothing to do with exploration or anything else. It is just trying to match the dynamics, but it's trying to match the dynamics in terms of the full distribution, rather than just trying to match the expectation of the next state. So if you would sample this,
Function by itself, it's like a Gaussian noise.
Yeah, so this thing does model indeed a probability distribution, yes. And the idea would then be that if you sample this thing over and over again, and this is also how you would typically then construct your loss to train this thing. If you would sample it over and over, you would like the outputs, the rewards and the next states that it outputs to match the distribution of rewards and next states that you would get from that state in action. So the simplest example is perhaps when the state and the action are fixed. Let's just take a very simple example where you're basically in a one-armed bandit where there's only one state, one action, and there is no next state, so we're just looking at the reward now. This is maybe the simplest example you could think of. The reward itself might still be noisy. And now you could learn an expectation model, which would be the expected reward, but you could also try to learn, it might for instance be a Bernoulli distributed reward. The other thing you might do is instead learn a function that actually randomly samples that Bernoulli with the same probability as the actual reward gets sampled. In that case, it might not be particularly useful to match all the complete distribution compared to the expected reward. But especially if you want to apply this to the sequential case where you want to sample these next states, then it might become more useful. Because then you can sample trajectories that are plausible, which is not necessarily the case if you have these expected states in the middle, because these expected states might not actually be, they might not correspond to any real states that you might encounter. Yeah?
So is the reason for using the noise term this way just to make it easier to learn the function, like the reparameterization trick?
So the question is whether the noise term makes it easier to learn the function. I would say we can, that's a separable question in a sense. Here I just wrote it down with the noise term because then you can write it down as an explicit function. If you have a different way to build a function that maps, or something that maps to a distribution, so from a state and action maps to a probability distribution, and then maybe you have a separate process that samples from that distribution, that's also fine. And in fact, these things might be, depending on how you look at it, might be equivalent, depending on how you draw the box, which is then labeled the p hat. So this thing now captures both the mapping it to a distribution and the sampling, where the sampling is regulated by this omega term. But you could, of course, separate these. You could have a separate component which tries just to map to the distribution, and it doesn't have any sampling. It just tells you the complete distribution, maybe some statistics of a parametric distribution like a Gaussian or something like that. And then you could separately sample from that. Effectively, how it would work in the software typically is that the sampling itself then still generates this omega and thereby constructs the actual sample that you get. There's a pseudo-random number generator and somewhere in there which generates this omega. But here I just made it explicit in the inputs. Okay. Now here's a third alternative, which is related to the previous one, but it's a little bit more explicit in the sense that we're going to learn the full transition dynamics, including the stochasticity. This is different from the previous one, because in the previous one we basically said we have this box, which takes a state and an action, and implicitly or explicitly takes a noise term, and it gives you a sample. In this case, we're not going to take that second step of sampling. We're just going to stop basically at the point where we have the probability distribution. So for any state and action, you need to supply an additional argument, which is the next state, and then it will tell you how likely that next state is. Or alternatively, maybe it could just give you the full distribution, like I said, in some parametric way. But in any case, we'll have something which you can write down as in this top equation as the p hats. It is a function in the sense of the state, action, and next states, and this should map to a probability. And in addition, this should sum to 1 over the next state. It should be a valid probability distribution. Of course, if you have an approximate model anyway, maybe that's actually something that you could violate. It's unclear whether you'd want to, but it's maybe something to keep in mind. But if you have that, so in this case I split the probability of the next state from the reward model. You don't have to do that. You could also try to learn the joint model in one go. But if you have those, you could basically plan all the way ahead. One way to do that is to use something like dynamic programming, which is more akin to the first equation here. Or if you want to know the value of a state many steps in the future, you can actually unroll this thing again and again and again, which effectively builds a big tree, where the branching factor of the tree depends on how many actions you have, but also on how many next states you have to consider. So this could be a very big tree. So it can be hard to iterate this explicitly, but they can still be useful. And indeed, if your number of states and actions isn't too big, you could at least do something like dynamic programming, where maybe you each time just take one step in the tree and then you back up using your approximate model. So what I'm saying is actually something that is maybe quite obvious in hindsight. What we've done here is we've basically just approximated the transition probabilities for the states and the rewards. And now here we're just assuming that these are the true MDP, and then we use them with our standard dynamic programming methods, for instance, to approximate values. So we had these three, let me just stop on this slide. We had these three ways to do models now. We could do the expectation model, we could do the sampling model, stochastic model, or also called generative model, or we could try to learn full model. And all of these cases are valid cases in some sense, and in some cases one might be more appropriate than the other, one might be easier to learn than the other. But then we still, of course, need to use them somehow to plan. Yeah?
Can we also do, can we also do full models for continuous state spaces?
Can you do full models for continuous state spaces, is the question. Yeah. You could, but of course these sums would turn into integrals. So then you bump into the issue of having to evaluate these integrals. There's ways to do that, like MCMC or other methods. You do have to keep in mind then that these are going to be approximations to the full integral in general. Of course, in certain specific cases, you might actually be able to analytically evaluate the integral, which might be better. But even if you do that, you should keep in mind that you're still analytically and therefore precisely evaluating something that depends on an approximation. So whether that's then so much better is unclear. So then there's an alternative which is quite obvious maybe in hindsight, which is, okay, you could just sample this thing, which is actually what MCMC does to evaluate the integral. And in some sense then we're back to the stochastic models again. So we have this probability distribution, but then in order to use it, we're going to sample from it, which is indeed a valid thing to do. And this means that we've basically went back and we learned the full model internally, but we did go back and do the stochastic model where we're sampling from this model. And then sometimes it's actually easier to sidestep this intermediate step of trying to learn the full model and just try to learn a generative model immediately with just having a loss on the samples rather than having an internal explicit representation of the probability distribution. Depends. Similarly, by the way, you can extend all of this to continuous actions in a similar way, where you could imagine that there's a continuous action space, but there might still be a probability distribution that might be relatively straightforward to learn. For instance, there might be a Gaussian that you can put around. Maybe your policy is a Gaussian, in which case you only need a few parameters to approximate this thing. And that's, of course, if your action is very high dimensional, but that's typically just a hard problem in any case. Okay. Now, I wanted to talk a little bit more about how you can then represent these. Well, I've mentioned a few of these already, but let's look a little bit more detail in for instance, whether you use a table lookup, which is of course only useful or possible in small problems, whether you use linear models or whether you use a deep neural network. And specifically, just to be also very concrete about what we're doing, let's look at the table lookup case. So in this case, the model is an explicit, finite Markov decision process. And one thing that you can then very easily do is to estimate these transition probabilities and these rewards by just tallying the actual transitions that you've made. So in this case, there's an indicator function here, which means that this is 1 whenever the arguments are all true, and it's 0 otherwise. So the first equation here basically says, for each time you've been in this specific state in action, you're going to add all the times you were in the next state, S prime on the left, which is bound on the right, and you're going to divide that by the number of times you were in this state in action in total. So this will be a number that is between 0 and 1, If you're always in the same next state, if this S prime is the state you always end up in, then this will become 1. If you're never there, then this thing will be 0. You're dividing by something which is non-zero. You're dividing by the number of times you were in this state in action, but you never went to this specific x prime, so then this probability will be 0. And in general, it will be between 0 and 1. And in addition, if you sum over all the possible s primes, all the possible next states, this will sum to 1, so it's a valid probability distribution. And here we separated out the reward from the transition again. And then the rewards could be similarly estimated, where in this case, there should have been an expectation here about, over the reward, because it, of course, could be random. Oh no, sorry, we're doing the sampling version here. So we're basically just looking at the reward, and whenever you were in that state in action, and you got a certain reward, you're going to average exactly those. So in this case, we're doing an expected reward, but we're learning those stochastic transition probabilities. And this is typically a relatively good idea in the sense that you don't necessarily have to keep the distribution of the rewards around, because we're not iterating on that. We don't need to sample the rewards necessarily in our model. In fact, you often get lower variance if you can just plug in the expected reward for each state in action. In general, the next states and the reward might be, there might be a joint distribution, and it might be better to model that one. But this is one way to construct a tabular model. Alternatively, one thing that you could also do is to use a non-parametric model as a stochastic model, which is something that is very easy and intuitive, I guess, in the tabular case. So what we're going to do then is keep around all of our past data in the simplest case. And whenever you want to sample from your model for a state in action, you're just going to look into your past state in actions, and you're going to pick one that matches that state in action. For simplicity, let's just now assume that you've done all actions in all states at least once, but you may have visited certain states multiple times and taken the same action there, so there might be multiple copies of the same state in action in your replay. But if there's at least one, then you can do this. You could query your replay buffer. You could look at the state in action that you're in right now, say, and you might just look in your replay buffer for every time you were in that state, you took that action, and you could look at the reward in the next state that occurred there. Now you could do two things. You could look at all the cases that this happened and then average over them, say, in which case you're doing an expectation model. Or you could just take the first one that you find, maybe randomly, and then in that case you would have a stochastic model. So this shows that there's some link between experience replay and model-based reinforcement learning, where you can think of the experience replay buffer as basically being a non-parametric model that stores experience samples rather than some explicit parametric representation. Of course, as you may have realized when I was saying this, when I was explaining how this works, it does come with a limitation, because if a state and action pair is not in your replay, then you cannot really sample meaningfully from it. You cannot say what the next reward and next state would be, which is of course very common. Let's say you're playing Atari and you have these pixel-based states. It might not be that likely, depending on the game that you're playing, it might not be that likely that you see the same frame very often, or that you've seen certain frames sufficiently often that they will be in your experience replay buffer. And in fact, because we want to explore, we would also be tempted to actually pick new states in states that, new actions in states that we've seen before, which means that there should be a lot of diversity in your replay. But you can still think of the replay, even in that case, as a non-parametric model that we're using somehow, and I'll get back to that in a moment. This is just an example. This is one we've seen before when we were talking about the difference between semaphore difference learning and Monte Carlo. It's the same experience that we had in that case. We've been in state A once, and when we were in state A, we saw a reward of 0, we transitioned to state B, and then we saw another reward of 0. Then we had a bunch of episodes that all started in state B. And in 6 of these 7 episodes, we saw a reward of 1, and in 1 we saw a reward of 0. Now, if we would apply these equations on the previous slide, we would build a model that basically looks like this, where in 100% of the cases we went from state A to B, And then in 75% of the cases, we transitioned with a reward of 1 and terminated. And in 25% of the cases, we transitioned with a reward of 0 and we terminated. Note that all the episodes ended with state B. So in this case, from state B, you always terminate. This might not be the real MDP, but it's the MDP that is consistent with the data. Any questions about this? Okay. Okay, so now we've talked about what type of model you might learn, how you might represent that model, and now of course we still want to use that model. So now, for now, we're going to assume that this p hat eta, it's built up from somewhere. You have it. And one thing that you could do is just sample from it and then use model-free reinforcement learning. It might be a little bit surprising because we're going to do model-based stuff. We're going to plan, but this is a form of planning. You're trying to build. Let me say it differently. One definition that you could of what you could call planning is you take a model and you output a policy. You output a plan, if you will. You could call that planning. If that is planning, then applying something like Q-learning to a model is a form of planning, because when you apply it, you will come up with a new policy, or a new plan, if you will. So you could call that planning. The only reason it's now called planning rather than learning is because we're doing it on the model rather than on the real environment, which of course is a little bit of a subtle distinction. So let's assume a generative model for now. We're going to sample experience from the model, and then we're just going to apply any model-free RL algorithm that we've discussed previously. And going back to the example that we just had, this could look like this, where we've constructed this, this model. And note that we can do this in basically 2 ways here. One is we can construct a parametric model using those equations that I had, where you basically just average the experience that you've had so far, which would end up with something that looks a lot like the thing here in the middle. Looks exactly like the thing there in the middle. Alternatively, we could just keep the experience around, and we could call it a non-parametric model, which in this case would be equivalent. And then we could sample from that. And the sampled experience might look like what you see here on the right, which is basically, in this case, just something that's fairly similar to a permutation of the experience we already saw on the left. There's a small distinction. See if you can find the difference. But if you would iterate on this long enough, and you would just use some model-free reinforcement learning algorithm, you would come up with the exact exact same answer. This is related to what we talked about before when we were looking at this example. I'll remind you what we were doing there, what we were discussing there. We were discussing the difference between temporal difference learning and Monte Carlo learning. And we were specifically discussing it in the context of batch learning, where you collect a certain amount of experience and then you iterate over and over again on that experience until convergence. And then we were talking about that the answers found by Monte Carlo differ from the answers found by temporal difference learning, which is still the case, by the way. But what we skimmed over in that case was that using the batch in full is basically a way to use a non-parametric model. Essentially, we've collected the experience and we were using that. We were thinking about the experience more and more without collecting new experience. And so this is what people then often call planning. Yes?
Right, so if 100% of the time, do you not need some probability of starting from A or B? Because you seem to be starting from B when you have a 100% probability of starting from A.
Yes.
Or, no, other subsets that may, sorry,
No, you touch upon something that's very good. So what we're not modeling explicitly, what we should be modeling explicitly, and what would be modeled implicitly when we just use the experience, is the start state distribution. So that's indeed something to keep in mind, and it is something that you should be modeling. If you just use the experience, it's there, right? It's in your experience, so it's already there. If you construct an explicit model, you should also basically construct that. And I skimmed over that. I basically just didn't talk about it. But it is something that's part of your model. Not just the transitions, but also where do you start when an episode ends. So that's a great question. Yeah?
Could you just repeat how batch learning is equal to thinking about the
Yes, so how is batch learning equal to planning in a sense? It's a good question. So the way to think about it is this. So the batch learning, as we talked about, this is a specific type of batch learning where we were just we were collecting some data, and then we would learn over and over on that batch of data. So we're not talking about, say, mini batches or something like that. We're talking about using the full batch of data and learning over and over on it. And what I'm saying here is that you could look at that batch of data, you could call that a non-parametric model. It's not going to be exact, but it is what you've seen so far. And then the going over and over on it, you could call that planning because you're not collecting any new data. So what we're making maybe a somewhat arbitrary distinction here between learning and planning, where we call it learning whenever we're collecting new experience and learning from that. And we call it planning whenever it just happens in the agent's head, in a sense. And if you're not collecting new experience, but you're just reusing the old experience, you're just in your head, in a sense. So then we might call that planning. If you're using model-free reinforcement learning algorithms to do the planning, they might not be aware of this, right? The algorithm might not know and might not care whether the data is real data or generated by a model. Okay. So traditionally, reinforcement learning algorithms do not store their experiences. The classic view is that some piece of experience comes in, you somehow use that, and then it's discarded. And then it becomes maybe easier to talk about model-free versus model-based because some of the experience is used for certain purposes, say to learn a value function or a policy, but you might not have an explicit dynamics model. But if you do use it to construct an explicit dynamics model, then we might call it model-based. So this is again going back to that terminology. But as I've mentioned a couple of times already, it's actually a little bit more gray than that. And maybe it's not so useful to make this sharp distinction anymore. So, so for the tabular case, I've already mentioned how batch learning is equal to, say, non-parametric model-based learning, and there's other equivalences. I also mentioned the second point here, that basically a replay buffer is a non-parametric model. It's a stochastic non-parametric model. If you just sample a certain state action and then you look at what the reward and next state were in that case, this will be a sample. So it's a generative non-parametric model, if you want to call it that. And more generally, you could think about using your experience in a variety of ways. One is you could take a sample, you could put it somewhere in a model. Maybe your model is a non-parametric experience buffer type model. Maybe there's also an explicit parametric model or one of these. Maybe you're also using it to update a value and the policy. And then it's unclear whether we want to call that model-based or model-free. So the distinction might disappear a little bit. In addition, there's this question about whether the word model is the most appropriate one. This goes back also to the question of whether we want to construct a model on the external state and actions or maybe on some other representation. And in fact, in statistics, we might use a much more broader term for the word model, where we might call almost anything that we're learning from the data a model. And in that sense, you could also call a value function a model. It's a model in a sense, it models the value. So there's another reason maybe not to go too much into that terminology. Or at least when you go into the terminology, when you want to talk about models and planning, it might be better to be a little bit more explicit about what you mean when you say model. What type of model? What are you actually learning and how are you actually using it? Okay, so why model-based at all, right? If we can just replay. Well, there's something nice about having a model, an explicit model, and that's that you can query it. And I'll talk more about that in this lecture, but I just wanted to make one, maybe, again, going back to the experience replay case, a somewhat clear connection there. If you can query a model, you might be able to ask for states and actions that are particularly useful right now to improve your policy. For instance, it might be your current state or action. Or you might have a policy or a value function, and that might induce a policy, and you might know it to be quite wrong in certain cases, and you want to improve it there using your model. This is something that you can't easily do if you don't construct any model, because then the experience that you learn from is tightly coupled to the experience that you gather, And for instance, you might just be in a certain situation which is nowhere near the states and actions that you can meaningfully learn about. You might be in a situation that you completely don't understand yet, so learning then is hard. Or you might be in a situation of which you basically have learned all that you could learn. And that's actually quite common because, say, if you have an episodic problem, what often happens is that you start at a certain start state, and then you learn about the region around that start state. And at some point, you've basically learned enough that you can branch out a little bit, and you start learning about the edge. But then whenever you restart an episode, you're in the region where you basically already know exactly what to do. And it's hard to learn more there. So first, you have to go all the way to the edge where the new things are, and then you could start learning again. But if you have a model, then you can query the model for the states and actions that are, in some sense, meaningful. And one potential thing, which is sometimes called prioritized sweeping. Prioritized sweeping is a more general term, but what is often done in practice there is that we sample certain states from our model which have a high error, say a high Bellman error, or a high sampled Bellman error, so a high temporal difference error. And then we replay those, or we query those from our model, instead of just randomly picking states and actions to learn from. And in a very related idea, this was applied to the Atari suite of games as well, and later to other things as well. You could do the same thing with the non-parametric model that is your experience replay, where you could replay things to learn more effectively, but you could prioritize which ones you look at, for instance, by looking at the estimation error you had in that state action when you last did an update from it. So each time you get a new piece of experience, you might update from it, but you'll also look at how big the update would be, and you put it into a prioritized experience replay where there's basically a queue that now has certain priorities on picking things. We're no longer sampling uniformly, but we're sampling according to some priority. And this turns out to work really well. It makes your value functions more accurate faster because you can focus your learning algorithm on the things that you can learn most about. So this is again a setting where we're using a non-parametric model, in this case the experience replay, and we're using a model-free algorithm, in this case Q-learning, or more specifically when applied to Atari, this was a variant of DQN that was used, to do the planning within that. Yes?
So that probably only works if we have non-parametric models, right? If we have a parametric model, if we are able to learn a parametric model, we probably already have learned a model-free policy that is good enough as well, right? Does that make sense?
So it's a good question. Yeah, the question makes sense. Let me rephrase it again to see whether I say the same thing. So the question is, does this mostly apply in a non-parametric case? But because in order to even learn a parametric model in certain states, you must have been there often enough in a sense that your values and policy are probably already quite accurate there. Now, why is that not the case? Because it's not the case necessarily. And the reason is that sometimes it's much easier to learn a model in a certain situation than it is to learn a value function, because you have two choices to learn a value function in the extreme case. You could either use Monte Carlo samples, which are multi-step, whereas your model could just be a one-step. And that might have very high variance. So the value function, if you're using Monte Carlo rollouts, if you use full trajectories from each state in action, might take very high variance inputs because they're looking at the long-term value, whereas the model might just look at the one step, which might be very easy to learn. Now, of course, there's an alternative, which is to use something more like temporal difference methods, which is the common case. And this is especially useful when you do planning because you can more easily perhaps do off-policy learning like Q-learning, where you're directly trying to estimate the optimal value function rather than for your current policy. But in that case, you're also learning a guess from a guess, so you're bootstrapping on a value that might not be accurate yet. So another reason to replay then, even if your model is completely accurate in that state, you might want to replay because the value estimates keep on changing and keep on updating. So going back to the Monte Carlo, because I didn't say something there, it might be important to say again, say as well. Even the Monte Carlo case is non-stationary because you'll be following a certain policy when creating that Monte Carlo rollout, and the policy might change because we're doing control. We're trying to optimize the policy. But if you think about the one-step model, which is conditioned on a state and an action, that's a stationary thing. So it might be much easier to learn that. Of course, this depends on the dynamics being easy to learn. If you think of a grid world, this is a nice example because it's often the case that you could basically just look at it like a 3x3 block around your agent, and you could construct a completely accurate model, which you could then use to plan with. Whereas it's unclear that you could as easily learn a value function. So it's a great question. Thanks for asking. Okay, so I think this is a good time to break for 5 minutes, and then I'll continue. So I mentioned this already, but it's good to stop and mention it a little bit more explicitly again, which is that there's a caveat. You might learn a model which is inaccurate for various reasons. One is you might have limited experience, so your model might not cover all the states that you might be interested in. Of course, you might also have a parametric model that has a certain capacity, which might not be able to fully capture the real dynamics, in which case you will have some, what we might call function approximation error in your model. And the important thing to note here is that your performance now, if you're going to plan with this, crucially depends on your model. To give you a very concrete toyish example of that, let's assume we've learned some dynamics model of a robot walking around in the real world, but the model has an error and it thinks there's a hole in the wall. And then if you plan with this model and you plan with it extensively, the policy that you might end up with will definitely go towards that hole in the wall that doesn't actually exist. So the question here that we also want to answer, at least partially, is how do you deal with that? How can you still plan when you have an inaccurate model? So one way you could go about this is just to not rely on it. Whenever the model is wrong, use model-free reinforcement learning. Additionally, or alternatively, a second approach might be that you could potentially reason explicitly about the uncertainty of your model. For instance, you could reason about the uncertainty of your parameters of the model. That's a very interesting and potentially powerful approach, but it's also hard in general. If you can meaningfully reason about the uncertainty of your model, this is a very promising approach, and it might actually also help you in exploration, because one thing that you could then do is to take into account the uncertainty of your model and, for instance, be a little bit optimistic with respect to the uncertainty when you select your policy to create new data. But in general, it's quite hard to do this, especially when the domain is very rich and the model might be very complex. And then the third approach, which I'll talk about a bit more, is to combine model-based and model-free methods. And in order to do that, we need to consider both of these sources of experience. So one source of experience is the standard thing. We have the true MDP. We sample our rewards and our next state somehow from this true MDP by just taking actions in the real world. And then we have the experience sampled from the model, where we also sample a reward in the next state, but now we do this from a parametric model. And then the model-free approach just learns from the first one, the model-based approach just learns from the second one. And now the maybe obvious thing to do is do both. And this is sometimes called DINA. This is how it's called in the book. This is something that Rich Sutherland proposed many years ago. The idea is to learn a model, as we discussed before, from the real experience, but then we learn and plan the value function from both the real and the simulated experience. So one way to go about that is to treat the real and the simulated experience equivalently as far as the model-free algorithm is concerned. So this just gets samples. It's indiscriminate on where the samples come from. And then it just tries to learn from that. So this goes back to this picture I showed before, where there's now experience that comes from the real world, and we're using it to directly update our value function, but we're actually going to learn a model and then use the data from that model to update the exact same value function. And this is a concrete algorithm. So we might initialize some, let's for simplicity just consider the tabular case. There's some finite set of states and actions, and we initialize a table of action values, Q, and we initialize a model where the model might be a deterministic one. So maybe we get a next state and a reward deterministically from this model whenever you give a state and action in. Just think of a grid world to have a concrete example in mind. And then how this algorithm works is that you're in a certain state, and then you might take a certain action. This is in the real state that you're currently in physically, say, and then you execute that action, and you will observe an actual next state and a reward. We just apply Q-learning. We're trying to optimize here, so we're just going to learn an action value that approximates the optimal action value using Q-learning. But then in addition, we're going to sample, the E here, it means we're going to update the model using the next state and the reward. If it's a fully deterministic model, we can just replace whatever was in the model for this state and action with the next state and the reward that you've seen right now. If they are already in there, if it's fully deterministic, then these will be the same. If there wasn't an entry yet in your model for these, then you will just put them in there. Of course, in general, you could have any other model updated. You update your model towards this sample of a next state and a reward. And then we have this additional step where we repeat a number of times, where this number is basically just a parameter of your algorithm. The following steps where you randomly sample some previously observed states and you randomly sample a previous observed action within that state. You query your model, you see what it gives as an output, a next state and a reward, and then you use that sampled experience to do a Q-learning update on the exact same value function. Now, one simple example of this is when you use a non-parametric model, a replay buffer, and this is exactly experience replay then. And in fact, this is what DQN uses, the algorithm that got applied to the Atari games, except that in the case of vanilla DQN, we might even skip the first step. We might not even use the data that you get right now. We just toss it into the experience replay, and then every once so often we sample a mini batch from the experience replay. Of course, you could, in addition, do the step with the most recent data, and it might be better. It's unclear. Might depend on other parameters as well. But this shows that there's a nice link here to algorithms that are used in practice as well. But of course, this is a little bit more general because the model doesn't have to be a replay buffer. It doesn't have to be a non-parametric model. It could be any other model as well. Yeah?
You don't run into bias with maximization bias with a stochastic environment in this case? Or can you just do double Q like you would?
Yes. So it's a good question. Don't you run into overestimation bias, for instance? You could run into any of the normal problems you might run into with Q-learning, and indeed you might just plug in double Q-learning here instead. And that's perfectly fine. In this case, we're just using Q-learning as an example of a model-free algorithm that you might apply, but you can use any other. You could also do multi-step things. You could also do policy iteration, maybe on a less fine grain, where you do an evaluation step, and then every once so often you improve your policy. All of these things are possible. So this is a concrete example of what might be called the Dyna-Q algorithm. Dyna as a term refers to the more general class of algorithms. In this case, Dyna-Q refers to the specific combination of Dyna with Q-learning inside. Just for the purposes of, this is also how it's defined in the book. Also just for the purposes of this slide and the next one. And so then, does this work? Does this help? Well, here's a simple example, simple grid world with the standard actions. And what this graph shows here at the bottom, you can look at it, it's in the book as well, so you can look at it at your leisure if you want. Down is better because what's on the y-axis is the number of steps per episode, and you're only rewarded when you enter the goal. And you basically want to minimize the number of steps until you reach the goal, so lower is better. And the top line there, which is where there's an arrow pointing with no planning steps, just uses Q-learning. And then there's a line way further down to the bottom which uses 5 planning steps, and there's one further that uses 50 planning steps. In each of these cases, this is per normal Q-learning update. Now, depending on how you look at this might seem a little bit an unfair comparison, because the 50 planning steps does basically 50 times as much compute. But of course, this depends on the trade-off on how expensive it is to gather real experience versus to how expensive it is to query your internal model and to learn from that. And there's many cases in the real world where gathering the real experience is the bottleneck. And it might be quite expensive and slow in some sense to gather new experience, whereas just querying the internal model or even the past stored experience might be much faster. So it depends on whether you're interested in pure compute versus sample complexity, and this shows that in terms of sample complexity, so the number of episodes that we've seen, it's much better to query your model. And this shows why this works. Yeah?
So are the planning steps equivalent of the n in the algorithm?
Yes. So the algorithm set repeat n times, and then 0, 5, or 50 is that n. And when you set n to 0, it just becomes Q-learning, because you're just not using the model. Okay, and this is now a visualization of why this helps. On the left there, we see basically the policy that was learned after the first episode by Q-learning. And we're doing one-step Q-learning, so basically the only value that was updated with anything that was not 0, with a non-zero reward, let's assume our action values were initialized at 0, the only one that had a non-zero update was the one leading it directly into the goal, where the reward is, say, +1. So in your next episode, this is basically not helpful at all until you reach that state just before the goal, and then you would update the state below that in your second episode. And then the third episode would again be completely blissfully unaware, and it would continue just randomly to explore the space until it enters that state, and slowly you build up this trajectory going backwards to the starting state over multiple episodes. Now, one way to go around it is to use multi-step returns, which we've discussed in the past. But in this case, we're just going to use the same one-step Q-learning algorithm, but we're going to plan. And what this does, it just samples states that you've seen before, including ones near to the goal, and it will update your action value function from this past experience, but now using the new action value estimates to bootstrap on. Because in each time when we do one of these updates, we're going to do a max Q in the next state, but we're going to use the current action value estimates there. Which means we can propagate information back. This is again during the second episode, so we've only ever seen the goal once, but already the model can propagate a lot of information all the way back and construct a policy that from many states leads very quickly towards the goal. The agent here is depicted as the black box, so you can see the agent in this right-hand side is not actually near where the model will tell it where to go, so it's basically just roaming around the start state randomly without going anywhere in particular. But while thinking about it, it gets more and more of a well-formed idea of how it should act when it enters one of these states. By the way, this picture here on the right-hand side, depending on how many actual updates we've done, would look similar to what you would get in the left-hand side if you just did many episodes, right? This is how you would construct your Q function then.
Sorry, what's the black mark?
Sorry? The black mark is where the agent currently is, physically. Because for each step of the agent, we'll do an update with that step. Near the goal, this won't actually change anything because the reward is 0 and your next state value is 0. But then we do 50 planning steps from arbitrary states from your past experience. So there's two things happening here. One is that we're doing many more updates using the model. And the other one is that we can query the model from any state. So we can update states that we're not actually physically in, because we've been there before. In this case, of course, the model is really simple. You only need to take an action in a certain state once to have an exactly accurate model for what the next state will be in that state. So this is a little bit of a toy example in that sense, but it does highlight a more generic maybe property of being able to plan. So another thing that you might want to do, I mentioned that it might be hard to use an inaccurate model if you rely on this fully. So now we're going to investigate that a little bit, and we're going to look at a situation where the model is going to be inaccurate, and we're going to enforce that basically by changing the environment without telling the algorithm. So we start off with the situation on the top left there, where it's a very simple grid world. You start at a certain state at the bottom, and the goal is to get to G, the goal. And of course there's a clear path there, and you might find it at some point. And the graph here at the bottom basically shows the learning progress. For now, just focus on this dyna-Q line. And at the beginning it's a little bit flat, and then at some point it goes up. And that's the cumulative reward that you've received So this must go at some point to a straight line that goes up, because you'll get a certain amount of reward, and the better you are at this task, the more reward you get per time step. But now, at time step 100, we're going to be a little bit mean to the agent, and we're going to change the environment by closing the gap that it was going through before, and we're opening a gap at the other side. And this is a tricky thing, because if you just think about the policy that was learned, or in this case, if you would just learn a value function without any model learning or whatnot, the value function would all point from the start, say, to the right. And it would take a very long time to correct for that, and to then explore, especially if you're doing something like epsilon greedy, you would have to just randomly wiggle your policy. And in addition, if you say from the start state would step one step to the left, the value function that you've learned will tell you to immediately go back right, because that was where you should be going. So at first you'll go back up to the place where the gap used to be. You might notice fairly quickly that you'll be disappointed there, that the values will go down, and at some point you will be less likely to go there perhaps. But if you haven't explored much to the left yet, it'll take a very long time for the agent even to randomly end up there, to maybe notice that now you can go through the wall there. The model-based algorithms, they have kind of the same problem, but because they can query their past experience, and they might randomly query all of the states and actions that you were in and keep on updating from them, they might more quickly learn this. One thing that they can very quickly learn is when they enter this state where the situation has changed. In this case, the model is deterministic, so only doing this once, they can notice that this is no longer a valid transition. Which means they only have to go towards where the gap used to be once, bump into the wall, and now their model is accurate again. At least at that part. They still have to discover the opening at the other end, so they still have to explore, but at least they very quickly learned that this is no longer the right place to go, and they can very quickly learn that all the values near where the gap used to be are actually much lower than you thought they were.
So how would a curve of non-dyna look like there?
That might be an interesting experiment. So around normal Q-learning here, see what happens. It's not on the I don't know how it would exactly look, it's not on the slide obviously. But it's something simple to code up, and it's quite interesting to look at. Here's a different situation.
So what is the difference between the three dynas?
So I'll say what dyna Q is, dyna Q plus is in a moment, but I first want to talk about this example. We're going to ignore dyna AC, which is also not in the new edition, I think. AC stands for actor critic, but we're basically just going to ignore that one. just ignore that line. This is a different situation, which might be in some sense a little bit harder. The reason being that we didn't close the gap. And the gap here used to be on the left rather than on the right. So you had to take this long detour around the left to go all the way to the goal. And at some point later on, a new gap opens, a shortcut appears, and now you can have a shorter path to the goal. Now the normal dyna Q agent doesn't actually see that. You can see that when we change that at time step 3000, the line continues to go up at the same gradient, which means that the agent still is taking the long way around to the goal, which is kind of fine, but it's not perfect. Of course, if we would close that gap, then it might learn to go towards the other way. But while we're not closing the gap, basically the algorithm thinks everything's fine. I might jitter a little bit, I might do a little bit of epsilon exploration around my trajectory, but I'm virtually never going to do enough exploration to take me all the way against my current best estimates towards this situation where I think there's no gap, just to find that there's a gap. Now what is this dyna Q plus agents? What this basically does, it gives a slight bonus in the model updates for states and actions that you haven't seen in a while. So if you haven't tried anything in a while, it'll basically try them again in the planning steps. It won't actually go there yet, but it will just assume somewhat optimistically that things got better over time. This means that every once so often the agent will actually go and try it again, just to see whether the model is still accurate. So what this bonus does, it basically tells you don't be too certain about your model, And in fact, the specific bonus tells you become more uncertain about your model if you haven't been in a situation for a while. And then we're basically going to be optimistic with respect to that uncertainty. We're going to say, I might just be able to do something here that I can't. I might just get a higher reward than I thought I would. And this is why the DynaQ plus agent curves up after a little while, because this means in its planning, it has been optimistic about trying things, and then at some point it'll actually go to the right and collect new data there, because it's optimistic that there might be something better there. The reward might be higher there than it was before, and if it wasn't the case, the model would quickly update again, and the uncertainty there would go down, and it would go back to the normal thing. But in this case, this is a good thing to do, and it'll try to go to that new gap, and it finds that there's actually a gap, and then it goes to the goal. Yeah?
Is the kind of optimism bonus, I guess, is that sort of a function of time until you've seen it, or is it just a bonus that occurs after a certain threshold?
It's a good question. In this case, the bonus is a function of time, so it increases over time as well. If you haven't tried a certain state action for a long time, the bonus will continue to grow until you finally go back and try it again. There's many choices in how you could do that, and what's particularly interesting but also challenging, and it's kind of an open problem, is how to do this when you don't have, say, a tabular situation in which you can just keep track of counts, but now you have, say, a very messy state space, and it's an open question how you could best do these bonuses then. Because it still seems like it's a good idea to have something of an optimism which depends somehow on your uncertainty. Yes?
Why is it that it doesn't underperform earlier?
Why doesn't it underperform earlier? Because it's exploration.
But it's not.
It is, kind of. So if you look very carefully, you can see that the DynaQ plus line was actually approaching the DynaCube line. At the beginning, it does a little bit better because the exploration is more informed. It's more directed. The DynaQ agent would randomly explore at the beginning, whereas the DynaQ plus agent would try to seek out novel situations already at the beginning, which is why the curve goes up faster at the beginning. It learns more quickly. But if you would keep on running this, the DynaQ plus agent would keep, and if nothing would change, the DynaQ plus agent would keep selecting non-optimal situations in order to keep on exploring. Depending on how you set up these bonuses, you can make that go away in the limit so that it only tries it for a limited amount. But if you assume that your environment might keep on changing, you don't actually want to do that. You want to keep on exploring. But that does mean that you incur a little bit of a hit, and these lines do actually approach each other before they branch off in this case. Yeah?
So in this example, like, it would need to say, I want to try the up action from like that right, like far right cell. But it can't just decide from the starting state, I want to try the action in this state, because it's 6 steps away from that. So it's also going to take like another 6 steps that it wouldn't normally take. So like,
how does it decide to go all the way to that corner when you just have, say, bonuses on your rewards? And the reason is because we're doing this planning step. Because let's just take this one transition there. You're on the top right there where there didn't used to be a gap, but now there's a gap, and we're considering that action, going up there, which is a bad idea at the beginning. So we haven't taken it in a while, and the reward there keeps growing and growing. Let's ignore for now the rewards in all the other states, which also play a role, but let's ignore them for now. And let's assume that your model otherwise is just the same old thing. Even then, because this reward keeps growing, the states that go into this state, you're going to update the value in that state, first of all, for the action going up. You're going to update it a little bit more optimistically. You're going to update it further up than it used to be. But then in your planning steps, even without going there, the states and actions that lead to that state would also begin to grow. So basically, the agent itself could keep on going to the left, going through this hole, but at some point, the optimism bias of going into the wall all the way at the top right would make its way all the way back to the start state, and you could imagine the agent, even if you're just giving a bonus on that specific action of walking into the wall there, the agent would at some point decide to go all the way there and go into it. Now, as I said, the other rewards actually also play a role, and what the agent will more likely do in practice is it will go a little bit in that direction. It will try one of the actions that it hasn't tried for a while, and then go back and do the normal thing. But that means that you've tried this one now, and the exploration bonus went down, which means that maybe what it'll try first, it'll bump its head against the wall, which is still there, a little bit closer to the start state, and then it will go back to the normal thing. But at some point, the values from these farther states have been visited that infrequently that the bonus starts to make its way all the way back and you do that again. Okay, now you can apply this with function approximation as well. What's hard is perhaps to find the true model in that case. And what's said here on the slide is essentially something I've said already. But it's basically just a hard and more or less unsolved problem. It's also a very active area of research, not necessarily specifically for reinforcement learning, but trying to create good generative models is a very active and fairly large portion of deep learning research nowadays. And I think many of these ideas might transfer to the reinforcement learning case, but it would be good to explicitly look at them and see how well these things then transfer. But it remains in essence just a hard problem to find good probability distributions in high dimensional feature spaces or input spaces. In addition, they could be quite computationally expensive, which means that it might take quite a bit of a compute to go from, say, a frame into a next frame, especially if you want to roll out multiple steps. But it doesn't mean it's not possible. By the way, just to call out again, there's the alternative of doing the replay, where you basically just sample a non-parametric model instead of having an expensive parametric model, which you could use here. But the idea is more general. So the idea of Dyna, even though we've looked at a tabular example, does apply to the function approximation case as well, where your model could be parametric or non-parametric, and you could still use that idea, and you could still potentially see similar gains as we've seen in these toyish examples, especially if your environment can be non-stationary, which is often the case when, for instance, there might be other agents in the environment, or whether when your policy just changes over time and new situations open up, or your agent just gains additional capabilities. It might be able to climb some steps that it couldn't climb before, so then it's useful to go back to the steps to try that again. Okay. So now we're going to turn towards, so we've been learning a model and planning with it and focus a lot also on how to deal with the inaccuracies. Now we're going to consider the setting where the model is given and we just want to use it. So normally, so what we did in Dyna is basically update a value function using all our standard model-free RL algorithms that we might want to use, and specifically we looked at Q-learning. Of course, we might also want to use a model to improve our policy, but then in particular we're actually interested in policy right now. We want to select an action, we want to select the best possible action that we can, and for simplicity it's good to keep in mind that the data collection might be the most expensive part of your whole system. So it's very important to select an action carefully, and you might be able to spend quite a bit of compute and effort in doing that. So it might be more important, as it says here, to make a more accurate local estimate of either your policy or the value function than you could feasibly get into your global estimate. This is also often what people intuitively think of when you say planning. We think of you're in a situation and you're going to look into the future in order to decide what you're going to do right now. This is a little bit different from the case of Dyna that we looked at just now, where we're basically doing this random planning all the time. We're just updating our complete value function in every state that we may have seen all the time to just make it more accurate. But now we're going to focus our compute. So that might look a little bit like this schematically. So a standard forward search algorithm starts at a certain state and then maybe plans through a whole tree. And these T's are maybe terminal states. So you might create this whole thing. You might have your MDP, you might do the full exhaustive search, and then you back all of that up and you find what the best decision was in this starting state. So the closed dots here depict actions. In this case, you have 2 actions in each state, and then you just try to find that thing. So you could use classical search algorithms. If the model is a true model, right, then it's okay to do that. The plan will be okay for the true model in that case. And there's many heuristics, especially that can speed that up quite a bit, so you don't have to build the full tree. But you could also, that could still be too expensive. The tree might be too big, in which case you could simulate. So this is very similar to the situation we were in before, except we're making the step of calling out explicitly that there's a model. before we basically just said, yeah, that's the environment, and we're just going to sample from the environment. But even if you have the model, it might be useful to simulate. And you might just create a trajectory. One difference between the model and the environment is that you could simulate multiple times, which you can't do in the environment. When you take an action, you've changed your state. You can't go back necessarily. But if you have a model, you could be in a state, you could consider multiple trajectories, and you could use those to update your value function before you actually select an action. So the idea is now that you basically start off with a certain state st, and then I'm using k here to denote the number of times you sample a trajectory. So we use our model, which might be an approximate model, might be the true model. In this case, we're kind of indifferent about that. And we're going to sample multiple trajectories. And one thing you could, for instance, do, you could just look at all the total returns across those trajectories, and you could average those. So in this tree, this looks a little bit like we don't just sample one of these, but we sample multiple, and we just maybe average over those. Alternatively, of course, you could use this trajectory to do something else like TD learning, in this case, for instance, SARSA, if you want to learn state action values. The search tree itself can be discrete. Even if your true environment is very messy and continuous or whatnot, especially if you think about the sampling version, it will actually have a state, and you'll actually have a next state, which is kind of a discrete quantification, quantization, what's the word there? I don't know, of the continuous problem, in which you can then do search. So this goes back to an earlier question about can you do this in continuous state spaces and continuous actions? Well, yes, you can. Especially if you do the sampling approach, you would actually still build a finite tree. So for model-free reinforcement learning, if you store everything in a table, that's a bit naive, because this is not always going to capture enough structure. Also, you're not going to generalize well. Either your table's too small, which means that each state maps to too many things in the real world, or your table is too big, which means you don't generalize, and very similar states have separate values that you need to learn separately, and everything will be slow. But if you do a simulation-based search, this is less naive, because you could actually build this up these trajectories. So you still don't generalize, so you might still want to learn a value function. You might want to use that in your tree. And I'll turn to that in a moment. But before we do, we just consider maybe the simplest case. This is what I said just now. We will consider a simulation policy. And this could just be a real policy right now. But you could, for some cases, you might want to consider something else. So we'll just call that the simulation policy. We'll start at a current state. We're just going to run this simulation policy multiple times, and then we're just going to average the returns. This is a simple thing you could do. What this will give you, in that case, is an estimate of the value of that policy. So we're not doing necessarily control in this case. We're just estimating the value of the policy. You could still use that for control if you do something like policy iteration. In some cases, it's also just very useful to know a value of a specific policy. There might be a certain set of policies that you're considering, and you might just want to estimate all of them, and you stand still for a while, you just run all of them through your model in your head, and then you pick, say, the one with the highest value before you actually take an action. Now, you could extend this very easily to action values rather than state values. So in the previous slide, we just had a V, and now I'm just going to replace the V with a Q, essentially. And then we can also select the real action very easily by just looking at for each of the actions we did these unrolls, say. So what we're going to do now is we're going to pick each of the actions, especially if there's like a small amount of actions actually, you can do that. And then we're going to follow after this action our simulation policy. And then for each of these actions we'll get an estimate. We'll do that multiple times, assuming the simulation is fairly cheap. Which means we get these action estimates for given this action and then following your simulation policy. This will be your value, or an approximation thereof. And then we can just pick the best action according to these approximated values. Note that these Q values are not stored anywhere, right? We're just computing them on the fly from a certain state and action right now in this specific setting. So we're constructing an estimate action value, but not to update a function right now, but just to use it immediately to select an action, using our model in the background to plan ahead. So this is a fairly pure case of model-based reinforcement learning where there's no explicit value function. We do need a simulation policy, which may or may not be explicit. It might just be a function of something else, might be random. But we're not explicitly constructing these action value estimates, which is also why a Q here is not parameterized. There's no parameter theta or anything. We're just constructing them. We take this one action in the end, and then we maybe recompute everything. We toss everything away, and we recompute everything at the next state. This is, of course, especially useful if planning is cheap. So you have a cheap simulator in your head, in a sense, but the real environment is expensive. This arrow, this wiggly thingy, it means that if you sample enough of these, it goes to that value. So it's kind of like in the limit of big K, it'll go there. It's pseudo notation. It's the LaTeX command leads to, if you yeah.
Can I understand this? It's just like reducing the computation, comparing to the like exhaustive search, because
Yeah.
we have the full. I mean, we assume we have the right full model of the MVP, so we don't want to compute all like the whole tree. So we just simulate K episodes, and then we like pick the optimal one.
Yeah, so this indeed, you can indeed view this as an approximation of computing the full tree. In expectation, any trajectory, the expectation of any of these trajectory will have the same value as doing the complete tree search, but the variance will be very high, which is why we sample multiple of them and then average over these. But indeed, if you just write out the expectation of any of these trajectories, it'll be the full tree. And then indeed you could compute that explicitly, but that's very expensive. So instead what we're going to do, we're just going to incur a little bit of variance. We're going to sample an amount. And then this K number might be very important in practice, because you want to sample sufficient amount of these to reduce the variance sufficiently that you pick a meaningful action. However, one thing that might be a little bit interesting here is you can do a little bit of, say, implicit exploration here, where you don't sample too many. And in that case, the action that you actually select will have a little bit of noise, which in some cases might be nice to induce a little bit of exploration, just using the variance of the returns.
Sorry. So in practice, like if we don't have if we have a wrong model,
Yeah.
so will we like update in the process, or I mean, if we have a wrong model, we will get the wrong estimation.
Yeah, so if you have the wrong model here, you get a wrong estimation. And in some sense, if there's multiple things you could do here, right? You could use the data that we've simulated here, still in a dyna-like sense, to also update a parametric value function. That's one, but leave that one aside. That's what we discussed before. The other thing you could be doing is you could be updating a learned model here. And that's actually completely consistent with this view, because we're not assuming that you have the true model here. We're basically saying there is a model, and we're going to use that to plan ahead and then to pick an action. And in some sense, if you've learned this model with the best of your capabilities on the data you've seen, it's going to be a little bit wrong, but it's also the best you have. But it's kind of okay, because you're going to select a new action, and you're just using this model to the fullest to select the next action. And then indeed what's missing from this slide is that you might still use the actual experience that you then get to update your model, to continue to update your model. And that's of course then very important. This part is kind of agnostic about whether you have an approximate model or a true model. You could do that in both cases. When you have a true model, the reason would be what you said first. Just to avoid computing the full tree, you might want to sample instead. Thanks. Okay. And now this sets us up to talk about something that's a little bit more sophisticated, which is Monte Carlo tree search. And it's a fairly similar thing to what we had before. We're going to we have a model, and this could be the true model, or it could be an approximate model. And we're going to simulate a number of episodes from the starting state. But now we're actually going to also explicitly build a tree containing visited states and actions. We're not going to build the full tree of all states and actions. I'll be a little bit more concrete about this in a moment. But then we're going to evaluate by looking at the past, basically experience that we built, and we're going to reuse some of that experience. It's maybe not too important to think about this equation right now. We're also running a little bit out of time. But we're going to reuse the experience explicitly, but we're also going to sample new experience with a new rollout. And then the action selection is basically the same. We're basically going to do the same principle, but I'll be a little bit more concrete about how this works then. But the principle is the same. We're going to sample stuff, and we're going to use that to select a new action. But instead, we now have two different parts. We have two different phases. The first phase sits within an explicit tree that we'll be building, and I'll show you that on the next slide, I think. Yeah, no, I'll show that a little bit later. I'll skip ahead to that slide. And we're going to store some information in that. So the easiest way to think about that is that there's a fixed start state. And this is why the next slide actually talks about Go, in which there is a fixed start state, which is the empty board. And then you could imagine building a search tree from that start state by simply slowly building up things that you've seen. We don't need to toss away all the information every time we restart. Maybe we can reuse that information sometime. Instead of just learning a model, and in fact in Go we might not learn a model, we might just use the actual dynamics of the game as a model. And then the second part is the same as we've seen before. At some point you're going to reach the end of that tree that you've built so far, and from there we're just going to sample. Within the tree, we can use a tree policy, which is potentially better informed because it can use all the past information that we had. In addition, it might also be because the tree is smaller. It might be more expensive because you take only a number of steps in there. And then the rollout policy could maybe be fully random. This has been tried in the past and is actually maybe more successful than you'd think it might be. Or it could be some faster policy that allows you to do many rollouts. And then the Monte Carlo tree search algorithm basically has four phases, four different parts of it. One is you're in your search tree and you're going to select actions according to the tree policy, which traverses your tree. This is a little bit similar to exhaustive search, where there's a smaller tree now because we're not considering the full tree, but we're going to consider a tree that we've built ourselves. And at some point we're going to reach the edge of the tree because the tree isn't full. We can't just go through the tree all the way until the end. At that point, we might expand the tree with one additional node. So this is an action you've taken in this state and we're going to add this to the tree. We don't have a value for this action yet. We haven't stored it yet. We've never maybe visited it before. So what we'll do to get a value for that action is going to do Monte Carlo rollouts. We're just going to roll out this rollout policy all the way towards the end, say in the game of Go, all the way until you win or you lose. You average maybe over multiple of these, and this gives you some estimate of what the value of that new expanded action is. And we're going to store that on the node. So now we have an approximate value for that action. And then we can back this up into the tree using classical backups that you might do whenever you do a tree search. You could think of this as like a dynamic programming like procedure, where you back up this value all the way to the root, maybe changing the values of the actions that led to this specific new node. And then you update the action values along the way as well. So you update the nodes along the way, not just the value of the action all the way at the root, but all the actions intermediate as well, with this new information that you have from the new rollouts. And then you could repeat this over and over again. Note that we're not adding all of the actions that we took in the rollout to the tree, just the first one. Otherwise the tree would grow very big very quickly, which would defeat the purpose. And so this was applied to Go, for which building a full tree is just too big. The branching factor is hundreds of potential moves, so only a few plies deep and you're already completely lost in terms of compute. This is just some standard Go stuff. You can play it on small boards or big boards. There's two players, white stones and black stones, not too important for what we're talking about. The important thing is there's only one reward function at the end. You either win or you lose. All the rewards along the way are 0. So it's fairly sparse. And then there's a policy that basically tells you how the one player moves and the other player moves. You might only have control over one of these. You might have a fixed opponent. And the value function is very simple. It's basically just, for a given policy, it's basically just the probability that you win. And the optimal value function is, of course, trying to maximize that probability that you win. And this is a simple example of then doing rollouts, where maybe you've done 4 games from a certain situation. Maybe you could think of the empty border at the top as the root. And if you just simulate rollouts, you might win sometimes, lose sometimes, and in this case, 1/2 of the time, so the value will be at half. But then the tree search would slowly build up a tree, and I'll just show you schematically, but I refer to the Sutton and Bartow book in which it's explained a little bit more in detail. So in this case, there's a root there at the top, and we only have one rollout which used the default policy, maybe random, and it happened to win. So now the value at the top there is 1. But now we expand this thing. We consider one more node in the tree from this top node. And from there, again, we just roll a random rollout to determine the value of this thing, and we happen to lose. So the value of this thing is now 0. 0 divided by 1 is 0. We also update the value at the root, which is now 1 divided by 2, because we won once and we lost once. So next time we might try something else. We try a different action. This time we picked something happily that won. So we update again the value of this state with the single rollout, which is now 1, because we've only done one rollout and it won. Typically you do multiple rollouts, but in this example we only do one. We also update the value at the root to now 2/3, because we've won twice, lost once. And then of course you might be tempted to try go from that same state again, and you expand from there. Not from the root this time, but from the state there below. You lose once, you update everything all the way back up the tree. Maybe you try something else, you win once, again you update all the way back at the tree. The total number of rollouts for the top is now 5, and 3 times we won, so the value of that state is now 0.6 for the specific policies that we've been following. Within the tree, we can use a more expensive and more elaborate policy because the tree is relatively small. The rollouts can be fairly long, so there we want something fast. For instance, a random policy. So typically the tree policy and the default policy, or rollout policy as it's also sometimes called, can differ, and they differ in practice. Okay. This was used in AlphaGo with some additional things. But basically now you have all the components. We've covered all the components in this course that you could now build your own AlphaGo system if you want. So there's of course many hidden details and many things that you would need to know in order to be able to do that. But the main core components are there. And maybe I'll just start the next lecture because we're running out of time. Maybe I'll just start the next lecture and then I can go in a little more detail how this works, because it's actually a very nice demonstration of combining all these components together. So for now, thank you.